Hi, my name is Precious Mahlelela. I'm a PhD candidate at the University of Cape Town, Oceanography Department. I will be giving a talk on circulating ocean. In this talk, we will look into the structure of the ocean. And then we will look into the two main types of ocean circulation, which is the wind-driven circulation and Thermohaline circulation. We will then look into how the ocean and atmosphere interact to make our planet habitable. In the beginning, we tested the hypothesis that distance and size is what made our planet habitable, and this was falsified. We then identified that what made our planet unique was the presence of the atmosphere, and we tested the role of the atmosphere in light and air. In the previous talk, we then investigated how the atmosphere moves to redistribute heat, in turn making our planet habitable. So this talk in a hierarchy of models still falls under moving atmosphere and ocean. We are still looking into how these bodies actually help redistribute heat across our planet and making it habitable. So the ocean is an important part of the Earth system because it covers 3/4 of the Earth's surface. It is a fluid and has a high heat capacity, meaning that it can absorb heat for a longer period without it reacting to the amount of heat that it has absorbed. Unlike the atmosphere, the oceans are heated from above, and thus causes stratification and triggers the movement of the oceans. I'm sure we've all heard about Charles Darwin, who has been coined the father of biology. Charles Darwin also contributed to the birth of our understanding on how oceans work and in the birth of oceanography as a field. So in one of his expeditions across the equatorial Pacific, Charles Darwin in these expeditions would collect salinity and temperature data, and he discovered very interesting patterns across the equator. This is the part of the globe that we have learned in our previous talk that receives the largest amount of solar radiation, and we would expect it to have the warmest temperatures. But what Charles Darwin discovered was that along the equator, temperatures were actually cooler than we would expect them to be, as highlighted in this diagram. So this is a figure of our global sea surface temperatures, and this is the color bar. So temperatures increase as you move from purple to red. So as you can see, in the equator, the sea surface temperatures are cooler than we would expect them to be. And this just sparked some interest into understanding why that is the case. And I hope by the end of this talk, you will have an understanding of what is happening there. This is the vertical structure of the ocean. And basically, you are cutting through the surface of the Earth. This is the southern hemisphere where we are, and that's the northern hemisphere. So as you can see, we have this red and blue shading. So these basically indicate temperature differences with the yellow, green, yellow, red, indicating increase in temperatures, while the blue shows cooler waters. So the first few hundred meters of the ocean is what we call as the mixed layer, and this is where most biological activity happens because this is the layer that interacts with the sun. So the sun rays don't penetrate to the deep ocean. They only can go up to the first 100 meters of the ocean, which is what we know as the mixed layer. This layer is also common with, but it has the highest biological activity. So there's a lot of organisms that thrive in this space, and therefore high competition for nutrients. And this layer is normally nutrient deficient because of the competition from organisms. And then at the bottom, we have what we call the picnic line. This is a layer of temperature and density change. And this is where we start to get cooler waters, and then we have the bottom waters. So for bottom waters, we've got two types. We've got two kinds. We've got bottom waters from the North Pole and from the South Pole. The northern bottom water is called the North Atlantic deep water, and from the South Pole it's called the Antarctic bottom waters. We will come back to this later, and I hope it will make more sense. So ocean circulation can be defined depending on your field of study as the net of all forces acting on the ocean, but an oceanography will define it as the large-scale movement of water on the ocean basin. And as I highlighted, there is two main kinds, which is the wind-driven and the Thermohaline circulation. So the wind-driven circulation, as the name suggests, is triggered by the movement of surface winds across the ocean. And this basically triggers movement of surface water, and what we see forming surface currents. And what we see here in this animation is just the different types of surface current, and you can see they are color coded. So the upper, and then deep, and water. So for the surface ocean, you get this red colored, which are warmer currents that tend to transport water from the equator towards the poles, while the bottom water one, the deeper or surface currents, tend to transport cooler waters from the poles towards the equator. I don't know if you can see it from this animation. So this wind-driven circulation leads to the formation of surface current, as I've highlighted, and we've seen two types of we've got the warm currents, which transport warmer waters from the equator to the poles, and the cold currents, which transport waters from the pole towards the equator. And the cooler surface currents are known as eastern boundary currents, while the warm currents are known as the western boundary currents. So what you can see, I'm not sure if it is, you can see that in South Africa, we're the only country in the world that has currents of contrasting temperature to our in our oceans, and this is known as this western boundary current is known as the Coriolis current, and it's found on the eastern part of South Africa. Then we have the eastern boundary current known as the Benguela current on the western part of the country. So we learned earlier in the course that objects suspended in the Earth's surface do not travel directly parallel to the wind, and this is because of a force introduced by the circulation of the Earth known as the Coriolis force. So the same thing happens to objects, or to objects in the ocean or with the ocean, and due to the circulation of the movement of the Earth, objects tend to be suspended to the left in the southern hemisphere and to the right in the northern hemisphere due to the rotation of the Earth. And this was first discovered noted by a gentleman known as Fridtjof Nansen in the northern seas, where he discovered that ice did not drift directly parallel towards the direction of the wind, but it tended to drift at an angle from the prevailing wind. And this was later investigated by Ekman, who realized that this was at a specific angle, which is a 45-degree angle from the direction of the prevailing wind, and this was named as the Ekman transport. So due to this, it was later then it helped understand what we observed in the equator. Because the prevailing wind in the equator, we learned that along the tropics, the prevailing winds are the easterlies, which blow from east to west. So what happens is, due to the Ekman transport, the surface waters are displaced at an angle which is 45-degree angle from the direction of the prevailing wind, which leads to the displacement, and that will be to the 45 degrees to the right in the northern hemisphere and 45 degrees to the left in the southern hemisphere, which leads to displacement of the surface water, and cold bottom water rises up to replenish this displaced surface water, leading to the cooler sea surface temperatures that were observed by Charles Darwin along the equator. And this process is known as upwelling. And so this is another figure that shows sea surface temperatures across the globe. And again, temperatures increase as you move from purple to red. And as you can see this is the temperatures that were observed by Charles Darwin. So this was found to not only occur along the equator, but to also occur in other coastal regions, which had the prevailing wind pushing surface water away from the coastal area. And so the circles just shows where these upwelling cells can be found. And one of them is found on the west coast of South Africa. So this figure shows chlorophyll, which is a measure of how nutrient rich the ocean is. And you can see that these parts of the ocean are found to be quite rich with nutrients. And this is important for the fish industry because fish like a nutrient-rich environment, and it's important. That's why we have the largest fish industry on the west coast of South Africa and towards Angola. So, like I have mentioned before, what makes South Africa special is that we have access to surface currents of contrasting temperatures, which is the warm western boundary current known as the Agulhas current to the east coast of South Africa, and the cooler current, which is the Benguela current on the west coast. And as you can see here, that the sea surface temperatures, this anime just shows sea surface temperatures through monthly sea surface temperatures throughout the year. You can see that it's always warmer on this side, while there are some changes on the west coast depending on the season. But these contrasting temperatures have implications on the type of climate that we experience in South Africa. On the eastern part of South Africa, we experience what we know as a tropical climate, and this is because of the close proximity to this warm current. So this climate is characterized by warm and wet summers, while it's cold. We experience cold and dry winters in the eastern part of the country. And on the western part of South Africa, we experience what we know as a Mediterranean kind of climate, which is associated with associated with wet winters and cooler and dry summers. But then what is most important is how, because of how the adjacent ocean, the type of vegetation that is present also on the landmass. So the green indicates vegetation cover. You can see that on the eastern part of the country, it's much greener compared to this part of the western part of the country, and this is just due to the adjacent ocean. So that was the wind-driven circulation. So the second main type of circulation is the Thermohaline circulation, and this one is basically driven by differences in salinity and temperature, which causes density differences. So what we get is that as warm surface waters are displaced towards the poles, they cool down and become more dense, and they sink, coming back as these bottom waters that we saw in the vertical structure. And this is because of the waters in the ocean do not mix because of these different density differences. So water in the equatorial Pacific, for instance, would be warmer, and then water molecules are more loosely packed, and that's making it lighter, and it will stay in the surface. But these deep waters, because of the water molecules are more packed together, then it becomes more dense, and it sits at the bottom. So this video just illustrates what happens when you try to mix two water bodies of different temperatures. So as you can see, you'll see that the water in the red is warm water with it's warm water, and while the water in blue is cold tap water. So let's just watch this for a bit. So when you try to mix the water of two different temperatures, you realize it will not mix because of the difference in density. While if you try the experiment with the waters having the same temperature, you will see that it will mix. You can even try that at home yourself. So because of these differences, it creates what we know as the Great Conveyor Belt. And the Great Conveyor Belt basically connects what happens on the surface to what happens in the bottom. And this is basically what we see. So the surface currents transport these warm waters towards the poles, where they cool, become more packed and dense, then they sink and then are brought in the northern hemisphere as the North Atlantic deep waters, and in the southern hemisphere as they brought back to the equator as the Atlantic border waters. And this process basically it suggests is that if a molecule can travel, if it's not taken out of the ocean, it can travel in this conveyor belt. across the globe through this conveyor belt, and this process is estimated to take about 1,000 years to complete. So we have learned that the ocean and atmosphere are important because they exchange momentum in order to create currents and thus distributing heat across the globe. But they also can regulate our weather patterns, and one way in which they do that is through a process of what we know as the El Niño Southern Oscillation phenomenon. So El Niño is basically the periodical changes in the easterlies along the equatorial Pacific. So this illustration just shows what happens along the equator in the equatorial Pacific. So we know that now that we have these easterlies that basically blow towards from the east to west. This is under normal conditions. So as much as most of the summer is displaced due to Ekman transport, but the net flow suggests that there will be more bulgy of warmer waters on the western side of the equatorial Pacific. And so this creates what we know as the Volca circulation. Because of these warmer waters on this side, you get more convection on this side, and that you have a low pressure system and more convection. Then on this other end of the equatorial Pacific, you have a high pressure system, creating this convective cell. And periodically, these winds relax along the equatorial Pacific. And when that happens, this whole system is shifted towards the center of the equatorial Pacific. And this shift causes changes in weather over the parts that normally received more rains during the normal condition, and the parts that received less rain during this normal condition. And in South Africa, during an El Nino, when these winds relax, we call that an El Nino condition, and it's the warm phase of this phenomenon. And in South Africa, during these times, we have droughts, while there is the other option is what we call the cold version, or the cold phase of this phenomenon, which is known as the La Nina condition. And this is basically an extreme version of the normal conditions where these winds are stronger than normal. And when that happens, we get droughts in South Africa. So this phenomenon is actually important because it regulates the climate in different parts of the globe, and this is how an example of how it is important for our ocean and the atmosphere to interact, because it actually does help in controlling the weather. So in this lecture, we have learned of the two types of circulation. Ocean circulation is the wind-driven, and the Thermohaline circulation. And we've learned that ocean circulation is important for heat distribution, and with upwelling being able to supply our fish industry, and how the ocean and atmosphere interaction helps in regulating our climate. And that South Africa is such a special place because we get to experience the best of both worlds. We have a warm current and cold current right at our footstep. Thank you.